Welcome to Sleepy Science Hub. I'm so glad you've joined me tonight for this gentle exploration of one of nature's most remarkable navigation systems. The sophisticated guidance abilities that allow a tiny honeybee to venture miles from her hive, navigate through complex landscapes, and return home with pinpoint accuracy using navigation techniques that rival the most advanced technological systems humans have ever created. As you settle in, let me know where in the world and at what time you're watching. Whether you're winding down as evening approaches or finding a quiet moment in the depths of night when the world feels still and peaceful, you discovered the perfect time to explore the fascinating world of bee navigation together. Now, get comfortable. Let your body relax into whatever surface supports you. Allow your breathing to slow and settle into a natural rhythm. And imagine yourself in a peaceful meadow on a warm morning, where the air is filled with the gentle hum of working bees as they begin their daily journeys of discovery and return. Tonight, we'll follow these remarkable creatures as they demonstrate navigation abilities that scientists are still working to fully understand, revealing how a brain smaller than a sesame seed can accomplish feats of spatial reasoning and environmental awareness that challenge our understanding of intelligence, memory, and the sophisticated ways that life has evolved to navigate the complex three-dimensional world around us. Take a slow breath. Feel yourself settling into this peaceful natural scene. And let's begin. In the gentle warmth of early morning sunlight, as dew still glistens on flower petals, and the air carries the fresh sense of a world awakening to a new day, a single honeybee emerges from the darkness of her hive and prepares for what will become one of nature's most remarkable demonstrations of navigation precision. This small creature, weighing less than 1/10 of a gram and measuring barely half an inch from head to tail, is about to embark on a journey that will take her several miles from home through landscapes that change constantly with weather, season, and time of day. Yet she will return with the same unerring accuracy that guided her ancestors for millions of years. The bee's emergence from the hive represents the beginning of a complex navigation sequence that starts with her very first perception of the world outside the familiar darkness of her home. Her compound eyes, each containing thousands of individual photoreceptors called ommatidia, immediately begin gathering information about her environment in ways that create a visual experience fundamentally different from human sight. Where we see smooth, continuous images, the bee perceives a mosaic of light patterns, color variations, and movement signatures that provide detailed information about distance, direction, and the characteristics of objects in her surroundings. The morning light itself becomes the bee's first navigation tool, as her visual system processes not just the brightness and color of sunlight, but also the polarization patterns that remain invisible to human eyes, yet provide the bee with directional information as reliable as a compass. Even when the sun itself is hidden behind clouds or trees, the polarized light patterns in the sky continue to provide navigational reference points that allow the bee to maintain her orientation and plan her route with precision that seems almost magical to observers who cannot perceive these hidden patterns in the light around us. The bee's preparation for flight involves a complex sequence of sensory calibration as she gathers information about current environmental conditions that will affect her navigation throughout the day. Her antennae, sensitive to chemical signals and air currents, sample the morning air for information about wind direction and strength, while also detecting the chemical signatures of flowers that may be blooming in different directions from the hive. This chemical information creates a kind of aromatic map of the surrounding landscape that complements the visual information her eyes are gathering. The physical act of taking flight represents a transition from the two-dimensional world of the hive surface to the three-dimensional aerial environment, where the bee will spend most of her active day. This transition requires immediate activation of navigation systems that must function perfectly from the moment of takeoff, as the bee begins integrating information from multiple sensory systems to maintain awareness of her position relative to home, while simultaneously identifying and evaluating potential destinations for her foraging activities. The bee's initial flight pattern reveals the sophisticated spatial reasoning that guides her navigation, as she typically begins with a series of orientation flights that spiral outward from the hive in gradually expanding circles. These orientation flights serve multiple purposes, allowing the bee to refresh her memory of local landmarks while also gathering updated information about current environmental conditions that may have changed since her last flight. During these orientation flights, the bee is essentially updating her internal map of the immediate area around the hive, noting any new obstacles, changes in vegetation, or shifts in familiar landmarks that could affect her navigation. The visual processing that occurs during these initial moments of flight demonstrates the remarkable efficiency of the bee's nervous system in handling multiple streams of complex information simultaneously. Her brain, despite containing fewer than 1 million neurons compared to the roughly 100 billion neurons in a human brain, processes visual information with speed and accuracy that allows her to navigate through complex three-dimensional environments while avoiding obstacles, identifying potential food sources, and maintaining constant awareness of her position relative to home. The bee's perception of color adds another dimension to her navigation abilities, as her visual system can detect ultraviolet light patterns that remain completely invisible to human eyes. These ultraviolet patterns create distinctive signatures on flowers, landscapes, and even the sky itself, providing the bee with navigation information that exists in a hidden spectrum of light that surrounds us constantly, but remains forever beyond human perception without technological assistance. The ultraviolet patterns on flowers serve as landing strips and directional markers that guide the bee to nectar sources, while ultraviolet reflections from leaves, water, and other landscape features create distinctive visual signatures that help the bee recognize and remember specific locations. The integration of visual and olfactory information during the morning flight creates a multidimensional awareness that combines the precision of visual navigation with the chemical information provided by scent trails and floral aromas. This sensory integration allows the bee to recognize not just where she is, but also what resources are available in different directions and at what distances, creating a comprehensive environmental awareness that guides her decision-making throughout the day. The morning air often carries the strongest scent signals, as flowers release their most potent aromas to attract pollinators during the cooler hours when volatile compounds remain concentrated rather than being dispersed by heat and wind. The bee's assessment of weather conditions during her morning emergence affects every aspect of her navigation planning for the day ahead. Her sensitive perception of air pressure, humidity, and wind patterns allows her to anticipate changes in flying conditions that might affect her ability to navigate accurately or return home safely. This weather awareness demonstrates a level of environmental sensitivity that enables the bee to make informed decisions about when to begin foraging, how far to venture from the hive, and when to begin her return journey to ensure safe arrival before conditions deteriorate. The social aspects of navigation become apparent as the bee observes and potentially follows other foragers who are beginning their own morning journeys. The information gathered from observing the departure directions and flight patterns of hive mates provides additional navigation data that can guide the bee toward productive foraging areas or help her avoid regions that other bees have already found to be unprofitable. This social information creates a kind of collective intelligence that enhances the navigation abilities of individual bees through shared environmental awareness. The bee's memory systems activate during the morning flight as she compares current sensory input with stored memories of previous successful foraging trips. This memory comparison allows her to recognize familiar routes, recall the locations of productive flower patches, and identify changes in the environment that might affect her navigation or the availability of resources. The remarkable spatial memory of bees enables them to remember the locations of hundreds of individual flowers and to revisit them in efficient sequences that minimize travel time and energy expenditure. The establishment of a home reference system occurs during the bee's initial orientation flights, as she calibrates her navigation systems to the current position of the hive and the environmental conditions that exist at the start of her journey. This home reference provides the foundation for all subsequent navigation, serving as the fixed point from which all distances and directions will be measured throughout her foraging expedition. The accuracy of this initial calibration determines the precision with which the bee will be able to navigate throughout the day and return home successfully. The morning flight also serves as an opportunity for the bee to practice and refine her navigation skills, as the relatively calm conditions and familiar surroundings provide an ideal environment for testing and adjusting her sensory systems and spatial reasoning abilities. This practice component of morning flights may be particularly important for younger bees who are still developing their navigation expertise, allowing them to gain experience in controlled conditions before venturing into more challenging or distant environments. The transition from orientation flights to purposeful foraging represents the moment when the bee's navigation systems shift from calibration and practice mode to active guidance of goal-directed behavior. This transition demonstrates the bee's ability to switch between different navigation strategies, depending on her current objectives, using broad area orientation when learning or updating her environmental awareness, and precise target navigation when traveling to specific known destinations. The bee's awareness of time becomes integrated with her spatial navigation during the morning flight, as she begins tracking the passage of time relative to her distance from home and the changing positions of environmental references like the sun. This temporal awareness will become crucial throughout the day as the bee calculates travel times, estimates the energy costs of different foraging options, and plans her activities to ensure adequate time for return flights before environmental conditions change or darkness approaches. The communication potential that begins with the morning flight sets the stage for one of the most remarkable aspects of bee navigation: the ability to share location information with hive mates through complex behavioral displays. The information gathered during morning flights may later be communicated to other bees through intricate dances that convey precise details about distance, direction, and resource quality, creating a social network of shared navigation knowledge that benefits the entire colony. The morning flight represents just the beginning of a daily navigation journey that will demonstrate some of the most sophisticated spatial reasoning abilities found anywhere in the natural world. As this tiny creature prepares to navigate with precision that rivals the most advanced technological systems, while using biological capabilities that evolution has refined over millions of years of adaptation to the complex challenge of finding resources in a three-dimensional world and returning safely home. High above the peaceful meadow where our honeybee continues her gentle morning exploration, the sun moves across the sky in its eternal arc, casting shadows that shift and change with each passing moment, yet providing our tiny navigator with the most reliable and sophisticated compass system that nature has ever devised. The relationship between honeybee and sun represents one of evolution's most elegant solutions to the challenge of maintaining directional orientation in a world where landmarks can be obscured, weather can change rapidly, and the need for precise navigation can mean the difference between a successful foraging trip and becoming hopelessly lost in an environment that extends far beyond the tiny creature's visual range. The bee's ability to use the sun as a navigation reference begins with her remarkable capacity to perceive not just the sun's position and brightness, but also the polarization patterns of skylight that remain invisible to human perception, yet provide a detailed directional map that extends across the entire dome of the sky above. This polarization compass works even when the sun itself is hidden behind clouds, trees, or other obstacles, as the polarization patterns in skylight maintain their directional relationships to the sun's position regardless of local weather conditions or environmental obstructions that might block direct sunlight from reaching the bee's visual system. The compound eyes of the honeybee contain specialized photoreceptors that function as biological polarization filters, detecting the orientation of light waves that vibrate in specific planes relative to their direction of travel. This polarization sensitivity creates a form of vision that adds an entirely new dimension to the bee's perception of her environment, overlaying the familiar world of colors, shapes, and movements with invisible patterns of light polarization that create a celestial navigation system of extraordinary precision and reliability. When morning sunlight first strikes the bee's visual system during her emergence from the hive, her polarization detectors immediately begin mapping the current orientation of the celestial polarization pattern relative to the sun's position in the sky. This initial calibration establishes the directional reference frame that will guide her navigation throughout the day, creating an internal compass that maintains its accuracy even as the sun continues its movement across the sky and the polarization patterns slowly rotate to follow the sun's changing position. The mathematical precision of the bee's sun compass demonstrates computational abilities that seem almost impossible to achieve with a nervous system containing fewer than 1 million neurons. Yet the bee effortlessly performs calculations that account for the sun's changing position throughout the day, the seasonal variations in the sun's path across the sky, and even the slight differences in solar timing that occur at different geographic locations. This temporal compensation allows the bee to maintain accurate directional references throughout extended foraging trips that may last several hours, during which the sun's position may change by dozens of degrees. The polarization patterns in skylight create what scientists call the polarization compass, a navigation system that provides directional information across the entire visible sky, even when only small patches of blue sky are visible through cloud cover or forest canopy. The bee's ability to read this polarization compass allows her to maintain her directional orientation even under environmental conditions that would completely disable navigation systems based solely on direct solar observation, demonstrating the robustness and reliability of this biological navigation system. The integration of polarization vision with the bee's perception of solar position creates a navigation system that functions like a biological GPS, providing continuous updates on directional orientation that remain accurate regardless of the bee's flight path, altitude changes, or the complex three-dimensional maneuvers that characterize her foraging behavior. This integration allows the bee to maintain awareness of her direction relative to home while simultaneously navigating toward distant food sources, avoiding obstacles, and responding to changing environmental conditions. The bee's sun compass operates with a precision that approaches the accuracy of human-made instruments, yet it functions automatically and continuously without requiring conscious attention or energy-intensive calculations. This effortless operation allows the bee to devote her conscious attention to other crucial tasks like flower recognition, nectar evaluation, and obstacle avoidance, while her navigation systems continue operating in the background with the reliability of biological autopilot systems that have been refined through millions of years of evolutionary testing. The adaptation of the sun compass to seasonal changes demonstrates the bee's remarkable ability to adjust her navigation systems to accommodate the changing patterns of solar movement that occur throughout the year. As seasons progress and the sun's daily path across the sky shifts to higher or lower angles, the bee's navigation system automatically recalibrates to maintain accuracy, demonstrating biological flexibility that allows the same navigation mechanisms to function effectively across all seasons and geographic locations where honeybees live. The compensation for geographic variations in solar patterns enables honeybee populations to maintain their navigation accuracy across the wide range of latitudes and climates where these remarkable insects have established successful colonies. From tropical regions where the sun passes nearly overhead to temperate zones where solar angles remain relatively low throughout the year, honeybees demonstrate the same navigation precision that suggests their sun compass systems include automatic adjustments for local solar patterns. The bee's ability to extrapolate the sun's position even when it is not directly visible represents one of the most sophisticated aspects of her celestial navigation system. Using polarization patterns, the bee can determine the sun's location even when it is hidden behind clouds, hills, or other obstacles, allowing her to maintain accurate directional references under a wide variety of environmental conditions that would disable simpler navigation systems based on direct solar observation. The internal chronometer that enables the bee to track time throughout her foraging expedition works in conjunction with her sun compass to provide navigation updates that account for the sun's continuous movement across the sky. This biological clock operates with remarkable precision, allowing the bee to predict the sun's future position and adjust her navigation calculations accordingly, ensuring that her directional references remain accurate even during extended foraging trips that span several hours. The backup navigation systems that complement the bee's sun compass include magnetic field detection and landmark recognition that provide alternative directional references when solar navigation is compromised by weather conditions or environmental obstacles. This redundancy ensures that the bee's navigation capabilities remain functional even under challenging conditions that might disable any single navigation system, demonstrating the biological wisdom of maintaining multiple independent navigation methods. The learning component of sun compass navigation allows young bees to gradually develop expertise in reading celestial navigation cues through experience and practice. This learning process involves both innate capabilities that provide basic sun compass function from the beginning of flight activity and acquired skills that improve navigation accuracy and reliability through repeated exposure to different environmental conditions and navigation challenges. The communication of solar navigation information to other bees represents one of the most remarkable aspects of honeybee social behavior, as successful foragers can share precise directional information based on sun compass readings through complex behavioral displays that convey solar bearings to nest mates who will use this information to guide their own navigation to distant food sources. This social sharing of navigation information amplifies the value of individual navigation discoveries and creates collective navigation knowledge that benefits the entire colony. The energy efficiency of sun compass navigation provides significant advantages over navigation systems that require continuous active sensing or complex calculations. The bee's polarization vision operates using the same basic visual processing systems that serve other visual functions, allowing sophisticated navigation capabilities to be achieved with minimal additional energy expenditure or neural processing capacity, demonstrating how evolution optimizes biological systems for maximum functionality with minimum resource requirements. The robustness of polarization-based navigation ensures reliable directional references even under environmental conditions that challenge other navigation systems. Cloud cover that obscures landmarks, atmospheric haze that reduces visibility, and changing light conditions throughout the day have minimal impact on polarization patterns, allowing the bee's sun compass to maintain consistent accuracy across a wide range of environmental conditions that occur during normal foraging activities. The precision of angular measurements achieved through polarization vision enables the bee to detect directional changes of just a few degrees, providing navigation accuracy that approaches the limits of what is physically possible with biological systems. This precision allows for highly efficient flight paths that minimize energy expenditure while maximizing foraging success, demonstrating how accurate navigation directly contributes to the bee's survival and reproductive success. The automatic operation of the sun compass allows the bee to maintain accurate directional awareness without conscious effort or attention, freeing her cognitive resources for other essential tasks like flower recognition, quality assessment of nectar sources, and social interactions with other foragers. This automation represents a crucial advantage that allows the bee to perform multiple complex tasks simultaneously while maintaining the navigation accuracy necessary for successful return flights to the hive. The calibration procedures that maintain sun compass accuracy involve regular comparisons between celestial navigation cues and familiar landmark references, allowing the bee to detect and correct any errors that might accumulate in her navigation systems. This ongoing calibration ensures that navigation accuracy remains high throughout extended foraging careers that may span thousands of individual flights and cover hundreds of square miles of territory. The integration of sun compass data with other navigation information creates a comprehensive spatial awareness system that combines celestial navigation with landmark recognition, odor trail following, and magnetic field detection to provide redundant navigation capabilities that ensure reliable guidance under virtually any environmental conditions. This integration demonstrates how biological navigation systems achieve reliability through diversity rather than depending on any single navigation method. The adaptation to different flight altitudes requires the bee's sun compass to function accurately, whether she is flying just above flower level or climbing to altitudes of several hundred feet to survey larger areas or avoid obstacles. The polarization patterns that provide directional references remain consistent across the range of altitudes used by foraging bees, ensuring that navigation accuracy is maintained regardless of flight elevation or the complex three-dimensional flight paths that characterize bee foraging behavior. The sun compass serves as the foundation for all other navigation systems used by honeybees, providing the primary directional reference that enables accurate operation of landmark navigation, distance measurement, and communication systems that depend on precise directional information. This foundational role demonstrates the central importance of celestial navigation in the bee's overall navigation strategy, and explains why the sun compass system exhibits such remarkable precision and reliability in its operation. Flowing beneath our honeybee like a living tapestry as she continues her gentle flight through the warming morning air, the landscape spreads out in an intricate pattern of visual features that create a navigation system as detailed and reliable as any map ever drawn by human cartographers. Each tree, flower cluster, shadow, and distinctive ground pattern becomes part of an elaborate visual vocabulary that the bee reads with extraordinary fluency, creating mental maps of remarkable precision that allow her to navigate through complex terrain with the confidence of someone following familiar streets in their own neighborhood. The bee's perception of landmarks operates through visual processing systems that extract and remember specific features from the continuous stream of images flowing past her compound eyes during flight. Unlike human vision that tends to focus on broad scenes and general patterns, the bee's landmark recognition system identifies and catalogs individual visual elements that remain stable and recognizable across multiple visits, creating a database of navigation references that can guide precise flight paths through environments that might appear featureless to human observers. The selection criteria that determine which environmental features become useful landmarks reflect the bee's remarkable ability to identify visual elements that provide reliable directional references while remaining consistent across different lighting conditions, seasons, and weather patterns. A distinctive tree with characteristic branching patterns, a cluster of rocks with unusual shapes, or a building with recognizable architectural features might serve as navigation landmarks, while features that change frequently or lack distinctive visual characteristics are ignored as unreliable for navigation purposes. The hierarchical organization of landmark information allows the bee to use different types of visual references at different scales of navigation, from large-scale features like hills or forest edges that provide general directional guidance over long distances, to small-scale details like individual flowers or ground patterns that enable precise positioning during the final approach to specific destinations. This multi-scale landmark system creates navigation capabilities that function effectively across the full range of distances encountered during foraging flights. The memory encoding of landmark information involves sophisticated neural processing that extracts the essential characteristics of visual features while filtering out variable elements that might change between visits. The bee's landmark memory focuses on geometric relationships, distinctive shapes, and spatial arrangements that remain stable over time, creating navigation references that maintain their usefulness across weeks or months of repeated foraging trips to the same general areas. The integration of landmark navigation with celestial compass systems creates a comprehensive spatial awareness that combines the global directional references provided by sun compass navigation with the local precision available through landmark recognition. This integration allows the bee to maintain accurate navigation, even when environmental conditions make one system less reliable than usual, demonstrating the biological wisdom of maintaining multiple independent navigation capabilities. The learning process for landmark recognition begins during the bee's first exploratory flights and continues throughout her foraging career as she gradually builds an increasingly detailed mental map of her territory. Young bees invest considerable time and energy in landmark learning flights that spiral outward from the hive in expanding patterns, carefully observing and memorizing the visual characteristics of features that will later serve as navigation references during goal-directed foraging trips. The visual processing algorithms that enable landmark recognition operate with remarkable efficiency despite the computational limitations of the bee's small nervous system. The bee's visual system can identify and remember hundreds of individual landmarks while maintaining the processing speed necessary for real-time navigation during rapid flight through complex three-dimensional environments, demonstrating optimization strategies that maximize navigation capability while minimizing neural resource requirements. The perspective independence of landmark recognition allows the bee to identify familiar features even when approaching from different directions or altitudes than during her original learning flights. This perspective flexibility requires sophisticated neural processing that can extract the essential geometric relationships of landmark features while remaining tolerant of the viewing angle changes that naturally occur during three-dimensional flight through varying terrain. The contextual relationships between landmarks provide additional navigation information that enhances the reliability and precision of landmark-based guidance. The bee learns not just the individual characteristics of specific landmarks, but also the spatial relationships between different features, creating a network of visual references that provide multiple independent confirmations of position and direction during navigation through familiar territory. The update mechanisms for landmark memory allow the bee to maintain accurate navigation references even as environmental features change gradually over time due to seasonal growth, weather damage, or human activities. The bee's landmark memory includes flexibility that can accommodate minor changes in familiar features while maintaining the essential spatial relationships that provide navigation value, ensuring continued navigation accuracy despite the natural evolution of landscape features. The robustness of landmark navigation under varying environmental conditions demonstrates the bee's ability to maintain visual recognition capabilities across the range of lighting, weather, and seasonal conditions that occur during normal foraging activities. Features that serve as reliable landmarks maintain their navigation value, whether observed in bright sunlight, cloudy conditions, or the different lighting angles that occur throughout the day and across seasons. The efficiency of landmark-based route planning enables the bee to select flight paths that optimize travel time and energy expenditure while maintaining navigation accuracy through terrain that may include obstacles, competing visual features, and areas with limited landmark availability. This route optimization demonstrates spatial reasoning capabilities that evaluate multiple navigation options and select paths that balance efficiency with reliability. The social aspects of landmark information sharing allow successful foragers to communicate not only the general direction and distance of food sources, but also specific landmark references that help other bees navigate to the same locations. This landmark information sharing creates collective navigation knowledge that enables multiple bees to use the same efficient routes and reduces the individual learning burden for bees visiting areas that have already been explored by successful foragers. The backup landmark systems provide alternative visual references when primary landmarks become temporarily unavailable due to seasonal changes, weather conditions, or temporary obstructions. The bee's landmark recognition system includes multiple overlapping reference points that ensure continued navigation capability even when individual features are obscured or have changed since previous visits. The precision of landmark-based positioning enables the bee to return to specific flowers or small areas with accuracy that often allows her to resume foraging within feet or even inches of her previous location. This precision requires landmark recognition systems that can detect and remember very small-scale visual features while maintaining the geometric accuracy necessary for pinpoint navigation in complex environments. The adaptation of landmark recognition to different habitats demonstrates the bee's ability to adjust her visual processing strategies to accommodate the characteristic features of diverse environments. Whether foraging in forest clearings with distinctive tree patterns, open meadows with scattered rock formations, or cultivated areas with regular field boundaries, the bee adapts her landmark selection and recognition strategies to utilize the most reliable visual features available in each specific environment. The temporal stability of landmark memory enables the bee to maintain navigation accuracy across the weeks or months of her active foraging career, demonstrating memory consolidation and retention capabilities that preserve spatial information for extended periods while allowing for updates and refinements based on repeated experience. This long-term landmark memory provides the foundation for the bee's growing expertise in navigating her territory efficiently. The resolution limits of landmark recognition reflect the constraints imposed by the bee's compound eye structure and nervous system capacity. Yet these biological limitations still enable navigation precision that rivals or exceeds many technological systems. The bee's ability to extract maximum navigation value from her sensory and computational resources demonstrates optimization strategies that achieve remarkable performance within the constraints of biological systems. The landmark verification processes that occur during navigation flights allow the bee to confirm her position and detect navigation errors by comparing current visual observations with stored landmark memories. This continuous verification ensures that navigation accuracy is maintained throughout extended flights and provides opportunities to correct course if environmental changes or other factors have affected landmark recognition accuracy. The integration of landmark information with distance and timing data creates a comprehensive navigation system that combines spatial awareness with temporal and energetic planning. The bee's landmark recognition system provides not just positional information, but also data about travel time, energy requirements, and resource availability that inform decision-making throughout her foraging activities. The landmark learning protocols that guide the bee's acquisition of visual navigation references involve systematic exploration patterns that ensure comprehensive coverage of her territory while optimizing the efficiency of information gathering. These learning protocols balance the need for thorough landmark documentation with the energy costs of exploration flights, demonstrating decision-making strategies that optimize long-term navigation capabilities. The error correction mechanisms in landmark navigation enable the bee to detect and compensate for recognition errors that might occur due to lighting changes, partial obstruction of familiar features, or confusion between similar visual patterns. These error correction capabilities ensure that navigation accuracy is maintained even when individual landmark observations are uncertain or ambiguous. The predictive capabilities of landmark-based navigation allow the bee to anticipate upcoming visual features based on her current position and flight direction, enabling proactive navigation adjustments that improve flight efficiency and reduce the cognitive load of continuous landmark monitoring. This predictive navigation demonstrates spatial reasoning that extends beyond simple landmark recognition to include understanding of landmark sequences and spatial relationships. The coordination between landmark recognition and flight control systems enables the bee to adjust her flight path smoothly and efficiently in response to landmark information, maintaining stable flight while processing visual navigation data and implementing course corrections. This coordination requires precise integration between sensory processing, spatial reasoning, and motor control systems that operate seamlessly during complex, three-dimensional navigation. The landscape reading abilities that emerge from sophisticated landmark recognition create a form of environmental literacy that allows the bee to navigate through her territory with the fluency of reading a familiar book, interpreting visual patterns that tell the story of direction, distance, and destination with precision that transforms the complex landscape below into a reliable navigation system that guides her safely through her daily journey of exploration and return. Within the gentle hum and bustle of the honeybee colony, where thousands of individual navigators coordinate their activities in one of nature's most sophisticated information-sharing networks, an extraordinary form of communication unfolds that transforms individual navigation discoveries into collective knowledge accessible to the entire community. When a successful forager returns from a productive flower patch located miles from the hive, she carries within her memory not just the nectar and pollen that will nourish her sisters, but also precise navigation information that she can share through one of the most remarkable communication systems ever discovered in the natural world, the waggle dance. The waggle dance represents far more than simple behavioral communication. It constitutes a sophisticated language that can convey complex spatial information with mathematical precision, encoding distance, direction, and quality assessments into a series of movements that other bees can observe, interpret, and translate into their own navigation instructions. This dance language operates as a biological information transfer system that amplifies the value of individual exploration and discovery by making successful navigation routes available to dozens or hundreds of other foragers who can benefit from one bee's successful journey. The initiation of a waggle dance begins when a returning forager enters the hive carrying information about a flower patch that warrants sharing with her nestmates. The decision to dance reflects the bee's assessment of multiple factors, including the quality of the nectar source, the distance traveled to reach it, the ease of navigation along the route, and the current needs of the colony for additional foragers. This decision-making process demonstrates sophisticated evaluation capabilities that balance individual experience with collective benefit. The basic structure of the waggle dance consists of a figure-8 pattern that the dancing bee performs on the vertical surface of the honeycomb, while surrounded by attentive sister bees who observe her movements with remarkable focus and attention. The central portion of this figure-8 pattern, called the waggle run, contains the essential navigation information encoded in the duration, direction, and intensity of the dancer's movements, while the return portions of the figure-8 allow the dancer to reset her position and repeat the information multiple times for maximum clarity. The encoding of distance information into dance movements operates through a precise relationship between the duration of the waggle run and the distance to the advertised flower patch. Longer waggle runs indicate more distant food sources, with a relationship calibrated so accurately that experienced observer bees can estimate travel distances with remarkable precision based solely on timing the duration of the dancing bee's central waggle movements. This temporal encoding of spatial information demonstrates mathematical relationships that rival the precision of human measurement systems. The directional information conveyed through waggle dance movements uses the angle of the waggle run relative to vertical as a direct representation of the flight direction relative to the sun's current position. When the dancing bee performs her waggle run straight upward on the vertical comb surface, she indicates that the food source lies in the direction of the sun, while waggle runs angled to the right or left of vertical indicate food sources located at corresponding angles relative to the solar direction. This angular encoding transforms three-dimensional flight directions into two-dimensional dance movements that can be precisely interpreted by observing bees. The intensity and vigor of waggle dance movements provide additional information about the quality and value of the advertised food source, with more enthusiastic dancing indicating higher quality nectar sources that justify longer flights and greater energy investment by potential recruits. This quality encoding allows observer bees to evaluate multiple dance advertisements and choose to follow only the most promising opportunities, demonstrating decision-making capabilities that optimize individual foraging success while contributing to overall colony efficiency. The acoustic components of waggle dancing add another layer of information transfer that enhances the precision and effectiveness of the spatial communication system. The dancing bee produces specific sound patterns during her waggle runs that provide additional details about the food source and help maintain the attention of observer bees in the crowded, noisy environment of the hive interior. These acoustic signals work in coordination with visual movement patterns to create a multimodal communication system of extraordinary sophistication. The learning process through which observer bees acquire navigation information from waggle dance displays demonstrates remarkable abilities to translate observed movements into personal navigation instructions. The observer bees must decode the dance movements, translate the directional and distance information into their own internal navigation systems, and then apply this acquired information to guide their own flight paths to food sources they have never visited. This learning transfer represents sophisticated cognitive processing that bridges the gap between social communication and individual navigation. The accuracy of information transfer through waggle dancing has been measured and confirmed through careful scientific study, revealing that bees recruited through dance communication can locate advertised food sources with precision that often brings them within meters of the specific flowers described by the original dancer. This accuracy demonstrates the remarkable fidelity of the dance communication system and the precision with which spatial information can be encoded, transmitted, and decoded through biological communication channels. The adaptation of dance communication to environmental conditions includes modifications that account for factors like wind speed and direction that might affect the flight experiences of recruited bees compared to the original dancer journey. Experienced dancers can adjust their directional and distance encoding to compensate for environmental factors that might otherwise lead recruited bees astray, demonstrating sophisticated understanding of how environmental conditions affect navigation and the ability to modify communication accordingly. The temporal aspects of dance communication reflect the dynamic nature of foraging opportunities and the need to coordinate colony-wide foraging activities with changing environmental conditions. Successful dancers may repeat their performances multiple times over several hours, with dance intensity and frequency adjusted based on ongoing assessments of food source productivity and colony needs. This temporal coordination ensures that recruitment efforts remain responsive to changing foraging conditions. The social dynamics surrounding waggle dance communication include complex interactions between dancers and observer bees that influence which dance advertisements receive attention and which food sources attract the most recruits. Popular dancers with particularly valuable information may attract larger audiences and generate more recruitment success, while less valuable opportunities may receive limited attention, demonstrating social selection mechanisms that optimize collective foraging efficiency. The integration of dance information with individual navigation capabilities allows recruited bees to combine the spatial information provided through dance communication with their own landmark knowledge, celestial navigation abilities, and environmental awareness to plan and execute successful flights to advertised food sources. This integration demonstrates how social information can enhance rather than replace individual navigation skills, creating combined navigation capabilities that exceed what either system could achieve alone. The error correction mechanisms in dance communication include multiple opportunities for observer bees to verify and cross-check the information provided by dancers, reducing the likelihood that navigation errors or misinterpretations will lead recruited bees to unsuccessful foraging trips. These verification processes may include observing multiple dance repetitions, comparing information from different dancers, and correlating dance information with independent environmental observations. The evolution of dance communication represents one of the most remarkable achievements in biological information transfer, demonstrating how natural selection can produce communication systems that approach the precision and efficiency of human language while operating through entirely different biological mechanisms. The waggle dance system exhibits characteristics of true language, including symbolic representation, referential meaning, and the ability to convey information about distant objects and locations. The cultural transmission of dance communication skills ensures that the ability to produce and interpret waggle dances is maintained across generations of bees within the colony, with young bees learning communication protocols through observation and practice rather than relying solely on innate behavioral programs. This cultural learning component adds flexibility and adaptability to the dance communication system that enhances its effectiveness across varying environmental conditions. The mathematical precision of dance communication encoding reflects underlying computational abilities that enable bees to perform complex spatial calculations and translate three-dimensional navigation experiences into symbolic movements that accurately convey spatial relationships. These mathematical capabilities demonstrate sophisticated spatial reasoning that rivals the geometric understanding exhibited by much larger-brained animals. The efficiency of dance communication as an information transfer system maximizes the value of individual exploration and discovery by making successful navigation routes available to many other bees without requiring each individual to invest time and energy in independent exploration. This efficiency multiplication effect enables honeybee colonies to exploit food resources more thoroughly and rapidly than would be possible through purely individual foraging efforts. The redundancy in dance communication systems provides multiple opportunities for accurate information transfer while reducing the impact of individual communication errors or misunderstandings. Multiple dancers may advertise the same food source. Observer bees can attend multiple dance performances, and dance information can be verified through independent navigation experiences, creating robust communication networks that maintain reliability even under challenging conditions. The geographic scaling of dance communication enables the system to function effectively across the full range of foraging distances used by honeybee colonies, from nearby flower patches located within a few hundred meters of the hive to distant food sources that may require flights of several miles. This geographic flexibility ensures that dance communication remains valuable across the diverse foraging strategies and territorial ranges exhibited by different honeybee populations. The seasonal adaptation of dance communication includes modifications that account for changing environmental conditions, food source availability, and colony needs throughout the annual cycle of honeybee activity. Dance communication patterns may shift in response to seasonal changes in flower blooming patterns, weather conditions, and the colony's requirements for different types of resources, demonstrating adaptive flexibility in social communication systems. The coordination between dance communication and other colony activities ensures that recruitment efforts remain integrated with broader patterns of colony labor allocation and resource management. The intensity and frequency of dance communication may be modulated based on factors like current honey stores, population size, and competing demands for forager attention, demonstrating sophisticated social coordination that optimizes overall colony function. Through the elegant movements of the waggle dance, individual navigation discoveries become shared knowledge that benefits the entire colony, transforming personal exploration into collective intelligence that amplifies the effectiveness of honeybee foraging while demonstrating one of nature's most sophisticated examples of spatial information sharing through biological communication systems that encode the three-dimensional world of navigation into symbolic movements of remarkable precision and beauty, invisible and imperceptible to human senses, yet as constant and reliable as gravity itself. The Earth's magnetic field flows through the air around our honeybee in gentle currents of magnetic force that have guided navigation for countless millions of years before the first compass was ever invented by human hands. This planetary magnetic field, generated by the flowing motion of molten iron deep within the Earth's core, creates invisible pathways through the atmosphere that our tiny navigator can detect and follow with sensitivity so refined that she can perceive magnetic variations too subtle for the most sophisticated human instruments to measure without careful calibration and shielding. The honeybee's magnetic sense operates through biological magnetoreception systems that remain among the most mysterious and fascinating aspects of animal navigation, involving cellular mechanisms that can detect magnetic field strength, direction, and even subtle variations in magnetic field characteristics that provide navigation information completely independent of visual landmarks, celestial references, or chemical signals. This magnetic navigation capability provides our bee with a backup guidance system that functions reliably even when other navigation methods are compromised by weather, darkness, or environmental obstacles. The discovery of magnetic navigation in honeybees emerged from careful scientific observations that revealed navigation behaviors that could not be fully explained by known sensory capabilities, leading researchers to investigate whether these remarkable insects might possess the same magnetic sensitivity that guides the epic migrations of birds, sea turtles, and other animals that navigate across vast distances with precision that suggests access to navigation information beyond the reach of conventional senses. The biological basis of magnetic detection in honeybees appears to involve specialized cells containing microscopic particles of magnetite, a naturally magnetic mineral that can function as biological compass needles within living tissue. These magnetite particles, arranged in precise orientations within specialized sensory cells, can detect the direction and strength of magnetic fields by responding to magnetic forces with mechanical movements that trigger neural signals, creating a biological interface between the invisible world of magnetic fields and the bee's nervous system. The integration of magnetic navigation with other sensory systems allows the honeybee to use magnetic information as either a primary navigation reference or as a backup system that provides independent confirmation of directional information obtained through visual or celestial navigation methods. This multi-sensory integration creates navigation capabilities that are more robust and reliable than any single navigation system could provide, ensuring accurate guidance even when individual sensory modalities are temporarily unavailable or providing conflicting information. The sensitivity of the bee's magnetic detection system enables her to perceive magnetic field variations that are orders of magnitude smaller than the Earth's main magnetic field, allowing her to detect local magnetic anomalies created by geological formations, metal objects, or even variations in soil composition that can serve as distinctive magnetic landmarks. This extraordinary sensitivity transforms the invisible magnetic landscape into a detailed navigation reference system that provides directional guidance and positional information completely independent of visual observation. The calibration of magnetic navigation systems occurs through processes that allow the bee to establish relationships between magnetic field characteristics and other navigation references, ensuring that magnetic information can be accurately integrated with visual landmarks, celestial compass readings, and spatial memory to create comprehensive navigation awareness. This calibration process demonstrates the bee's ability to cross-reference multiple navigation systems and maintain accuracy across different sensory modalities. The magnetic declination compensation that enables accurate magnetic navigation requires the bee to account for the difference between magnetic north, as indicated by the Earth's magnetic field, and true geographic north, which varies depending on geographic location and changes slowly over time due to variations in the Earth's magnetic field. This compensation demonstrates sophisticated spatial reasoning that can maintain navigation accuracy despite the complex relationship between magnetic and geographic coordinate systems. The temporal stability of magnetic navigation provides the bee with a navigation reference that remains consistent across daily and seasonal cycles, unlike solar navigation, which requires continuous compensation for the sun's movement, or landmark navigation, which may be affected by seasonal changes in vegetation or weather conditions. This temporal stability makes magnetic navigation particularly valuable for maintaining directional orientation during extended flights or when other navigation systems are temporarily unreliable. The resolution of magnetic navigation enables the bee to detect directional changes and position variations with precision that approaches the accuracy of her other navigation systems, despite the relatively weak strength of the Earth's magnetic field compared to other environmental stimuli. This resolution demonstrates the remarkable sensitivity of biological magnetoreception systems and their optimization for detecting subtle variations in magnetic field characteristics. The backup navigation function of magnetic sensing becomes particularly important during challenging environmental conditions when primary navigation systems may be compromised by factors like heavy cloud cover that obscures celestial references, atmospheric haze that reduces landmark visibility, or unfamiliar territory where landmark information is limited. Under these conditions, magnetic navigation can provide essential directional guidance that enables continued navigation toward destinations or safe return to the hive. The magnetic anomaly detection capabilities of the bee's magnetoreception system allow her to identify and potentially use local variations in the Earth's magnetic field as distinctive navigation references. Geological formations, mineral deposits, or human-made structures that create local magnetic disturbances can serve as magnetic landmarks that provide positional information independent of visual features, creating opportunities for navigation in environments where visual landmarks may be scarce or unreliable. The interference resistance of biological magnetic navigation systems enables the bee to maintain magnetic sensitivity despite exposure to artificial magnetic fields created by human technology, power lines, electronic devices, and metal structures that might be expected to disrupt magnetic navigation. This interference resistance suggests that biological magnetoreception systems include mechanisms for filtering out artificial magnetic disturbances while maintaining sensitivity to natural magnetic navigation signals. The learning component of magnetic navigation involves the bee's ability to establish associations between magnetic field characteristics and successful navigation outcomes, allowing her to refine her use of magnetic information based on experience and improve the accuracy of magnetic navigation through repeated exposure to different magnetic environments. This learning demonstrates that magnetic navigation is not purely instinctive, but can be improved through practice and experience. The coordination between magnetic sensing and flight control systems enables the bee to translate magnetic directional information into appropriate flight path adjustments without conscious attention to the magnetic navigation process. This automatic coordination allows magnetic navigation to operate as a background guidance system that provides continuous directional references while the bee's conscious attention remains focused on other important tasks like flower recognition, obstacle avoidance, and environmental monitoring. The geographic variation in magnetic navigation reflects the bee's ability to adapt her magnetic sensing to the different magnetic field characteristics that occur at different locations around the world, where variations in magnetic field strength, inclination, and declination require corresponding adjustments in magnetic navigation strategies. This geographic adaptability ensures that magnetic navigation remains functional across the wide range of environments where honeybees have established successful populations. The magnetic field mapping capabilities of the bee's navigation system may enable her to develop mental representations of magnetic field variations across her territory, creating magnetic maps that complement her visual landmark maps and provide additional navigation references that can guide efficient flight paths and accurate position determination. These magnetic maps would represent a completely invisible landscape that exists parallel to the visible environment, yet provides equally valuable navigation information. The storm compensation mechanisms in magnetic navigation allow the bee to maintain navigation accuracy even during geomagnetic disturbances caused by solar activity that can temporarily alter the Earth's magnetic field characteristics. These compensation mechanisms demonstrate the robustness of biological magnetic navigation and its ability to function reliably even when magnetic field conditions deviate from normal patterns. The precision of magnetic direction sensing enables the bee to detect angular variations in magnetic field direction that provide navigation accuracy comparable to other direction-finding systems, despite the fact that magnetic field lines are invisible and must be detected through biological sensors rather than direct observation. This precision demonstrates the remarkable capabilities of biological magnetoreception systems and their optimization for navigation applications. The integration of magnetic navigation with memory systems allows the bee to store magnetic field information along with other navigation data, creating comprehensive spatial memories that include magnetic characteristics of familiar locations and routes. This integration enables the bee to use magnetic information for route recognition, position confirmation, and navigation planning based on stored memories of magnetic field patterns associated with successful previous flights. The energy efficiency of magnetic navigation provides significant advantages over navigation systems that require active sensing or continuous computation, as magnetic field detection can operate using minimal energy while providing continuous directional references. This efficiency allows magnetic navigation to function throughout extended foraging flights without depleting the bee's energy reserves or interfering with other essential physiological processes. The redundancy provided by magnetic navigation enhances the overall reliability of the bee's navigation system by providing independent confirmation of directional information obtained through other methods, reducing the likelihood of navigation errors and providing backup guidance when primary navigation systems are compromised. This redundancy demonstrates the biological wisdom of maintaining multiple independent navigation capabilities rather than relying on any single guidance method. The developmental aspects of magnetic navigation involve the maturation of magnetoreception capabilities as young bees gain experience with different magnetic environments and learn to integrate magnetic information with other navigation systems. This developmental process ensures that magnetic navigation becomes increasingly reliable and accurate as bees accumulate flight experience and exposure to varying magnetic field conditions. The social aspects of magnetic navigation may include the sharing of magnetic navigation information through behavioral communication or collective navigation behaviors that allow multiple bees to benefit from shared magnetic sensing capabilities. While less obvious than the visual communication demonstrated in waggle dancing, magnetic navigation information may be shared through subtle behavioral cues or coordinated flight patterns that enhance collective navigation success. The evolutionary significance of magnetic navigation in honeybees reflects the ancient origins of magnetoreception capabilities that have been refined through millions of years of natural selection to provide reliable navigation guidance across diverse environments and geographic regions. This evolutionary heritage demonstrates the fundamental importance of magnetic navigation for survival and reproductive success in species that depend on accurate spatial orientation for foraging, migration, and territorial navigation. Through the subtle detection of invisible magnetic whispers that flow constantly through the air around her, our honeybee maintains connection to one of the Earth's most fundamental force fields. Using magnetic navigation capabilities that link her tiny biological compass to the grand magnetic systems generated by our planet's molten core, creating navigation abilities that operate on principles as ancient as the Earth itself, yet as immediate and practical as the need to find her way safely home. Drifting through the gentle morning air like invisible ribbons of information, chemical signals create a hidden landscape of scent that surrounds our honeybee with navigation guidance as reliable and detailed as any visible map, yet operating through molecular messages that travel on every breeze and settle on every surface to create an olfactory navigation system of extraordinary sophistication and sensitivity. The bee's ability to detect, interpret, and follow these chemical trails represents one of nature's most elegant solutions to the challenge of maintaining spatial orientation through information that can persist in the environment long after the original source has moved on, creating navigation pathways that guide successful return journeys through scent memories that linger in the air and on familiar landmarks. The chemical navigation system that guides our bee operates through olfactory capabilities that far exceed human scent detection, enabling her to perceive molecular concentrations so low that they would be completely undetectable to us, while simultaneously distinguishing between hundreds of different chemical compounds that create distinctive scent signatures for flowers, landmarks, other bees, and the hive itself. This chemical sensitivity transforms the invisible world of airborne molecules into a detailed information network that provides navigation guidance, resource location, and social communication through channels that remain completely hidden from human perception. The production of navigation pheromones begins within the bee's own body through specialized glands that can release distinctive chemical signals during flight, creating personal scent trails that mark her route and provide chemical breadcrumbs that can guide her return journey along familiar pathways. These self-generated navigation aids demonstrate the bee's ability to modify her environment in ways that enhance her own navigation success, leaving behind chemical markers that transform anonymous landscapes in a personally familiar territory marked with her own molecular signature. The detection of floral scent plumes allows the bee to locate flower patches from considerable distances by following concentration gradients of volatile compounds that flowers release to attract pollinators. These scent plumes create invisible highways in the air that can guide the bee toward rewarding food sources even when the flowers themselves remain beyond visual range, demonstrating how chemical navigation can extend the bee's effective foraging radius far beyond the limitations imposed by visual detection alone. The memory encoding of scent information involves sophisticated neural processing that can associate specific chemical signatures with successful foraging outcomes, creating olfactory memories that guide future navigation decisions and route selection. The bee's scent memory system can store information about hundreds of different chemical combinations, allowing her to recognize and navigate toward familiar flower types, productive foraging areas, and important landmarks based solely on their distinctive chemical signatures. The integration of chemical navigation with visual landmark recognition creates comprehensive spatial awareness that combines the precision of visual positioning with the range and persistence of chemical information. Scent markers associated with visual landmarks enhance the reliability of landmark recognition while extending the effective range of landmark-based navigation, creating hybrid navigation systems that leverage the advantages of both visual and chemical information sources. The persistence of chemical navigation signals provides significant advantages over other navigation systems that require continuous environmental input, as scent trails and chemical markers can remain detectable for hours or days after their initial deposition, creating navigation aids that continue functioning even when the bee is not actively producing or refreshing the chemical signals. This persistence allows chemical navigation to provide guidance for return trips along routes that were chemically marked during outbound journeys. The directionality of scent trail following enables the bee to determine not just the presence of chemical navigation signals, but also the direction of increasing or decreasing concentration that indicates the path toward the source of chemical markers. This directional sensitivity allows the bee to follow scent trails toward their origins or to navigate away from chemical sources depending on her current navigation objectives, creating bidirectional navigation capabilities that enhance the flexibility of chemical guidance systems. The chemical communication of navigation information occurs when successful foragers deposit pheromone markers along productive routes, creating shared chemical pathways that can guide other colony members to the same rewarding destinations. These shared scent trails create collective navigation infrastructure that benefits multiple bees while reducing the individual exploration costs required to locate and navigate to productive foraging areas. The discrimination between different chemical signals allows the bee to distinguish between navigation pheromones produced by members of her own colony, chemical markers left by bees from other colonies, and the natural chemical signatures of flowers and environmental features. This discrimination capability ensures that chemical navigation remains accurate and relevant, while preventing confusion that might result from following chemical signals that are not relevant to the bee's current navigation objectives. The temporal aspects of chemical navigation reflect the changing concentration and composition of scent signals over time, as chemical markers gradually disperse, degrade, or become overlaid with newer chemical information. The bee's ability to assess the age and reliability of chemical navigation signals allows her to prioritize recent, strong chemical markers while appropriately discounting older or weaker signals that may no longer provide accurate navigation guidance. The environmental modulation of chemical navigation involves the bee's ability to account for weather conditions, air currents, and atmospheric factors that affect the distribution and concentration of chemical signals. Wind patterns can disperse scent trails, humidity can affect chemical volatility, and temperature changes can alter the rate of chemical degradation, requiring sophisticated interpretation of chemical information that considers current environmental conditions. The range limitations of chemical navigation reflect the physical constraints of molecular diffusion and atmospheric dispersion that limit the distance over which chemical signals can provide useful navigation information. While chemical navigation excels at providing guidance over short to medium distances, particularly in areas with limited air movement, it typically functions as a complement to rather than replacement for longer-range navigation systems like celestial compass navigation. The specificity of chemical recognition enables the bee to identify not just general categories of chemical signals, but also subtle variations in molecular composition that can indicate specific flower species, individual plants, or even particular regions within flower patches. This chemical specificity creates navigation capabilities that can guide the bee to precisely the types of resources that will be most valuable for her current foraging objectives. The social coordination through chemical signals allows multiple bees to share navigation information through coordinated pheromone marking that creates collective chemical maps of productive foraging areas. These social chemical navigation systems can evolve over time as multiple bees contribute to and refine shared scent trails, creating navigation infrastructure that represents the accumulated exploration and success of many individual foragers. The backup navigation function of chemical signals provides alternative guidance when other navigation systems are compromised by environmental conditions, equipment failure, or challenging terrain. Chemical navigation can function effectively during periods of cloud cover that compromise celestial navigation, in areas with limited visual landmarks, or when magnetic navigation is disrupted by local anomalies, demonstrating the value of maintaining diverse navigation capabilities. The personal scent signature that each bee carries creates opportunities for individual recognition and tracking that can enhance social navigation and communication within the colony. The bee's personal chemical signature allows her to recognize her own scent trails, distinguish her markers from those of other bees, and potentially communicate individual identity information through chemical signals that other colony members can detect and interpret. The chemical route optimization occurs when the bee uses scent information to evaluate and compare different potential flight paths, selecting routes that offer the most favorable combinations of chemical signals indicating resource availability, landmark recognition, and navigation reliability. This optimization demonstrates decision-making capabilities that integrate chemical information with other navigation data to select the most efficient and successful navigation strategies. The learning enhancement through chemical associations allows the bee to improve her navigation accuracy by forming connections between successful foraging outcomes and the chemical signatures associated with productive routes and destinations. This chemical learning creates increasingly sophisticated navigation capabilities that reflect the accumulated experience of successful chemical navigation across multiple foraging expeditions. The error correction mechanisms in chemical navigation enable the bee to detect and compensate for situations where chemical signals may be providing misleading or outdated information due to environmental changes, chemical degradation, or confusion between similar chemical signatures. These error correction capabilities ensure that chemical navigation enhances rather than compromises overall navigation accuracy. The seasonal adaptation of chemical navigation involves adjustments to scent detection and interpretation that account for changing chemical signatures as flowers bloom and fade throughout the growing season. Environmental conditions affect chemical volatility and persistence, and the colony's resource needs shift in response to seasonal cycles. This seasonal flexibility ensures that chemical navigation remains effective across the full annual cycle of bee activity. The precision of chemical source location enables the bee to use scent information not just for general directional guidance, but also for pinpoint navigation to specific flowers or small resource patches that might be difficult to locate through visual search alone. This precision demonstrates the remarkable spatial resolution that can be achieved through chemical concentration gradients and molecular tracking capabilities. The integration of chemical navigation with flight control systems allows the bee to automatically adjust her flight path in response to chemical signals without conscious attention to the chemical navigation process, enabling seamless integration of chemical guidance with other navigation systems and flight behaviors. This automatic integration allows chemical navigation to operate as a background guidance system that enhances overall navigation performance. The chemical memory consolidation that occurs after successful foraging trips strengthens the associations between chemical signatures and navigation success, creating long-term chemical navigation capabilities that improve over time as the bee accumulates experience with different scent environments and chemical navigation challenges. This consolidation process demonstrates how chemical navigation skills develop and improve throughout the bee's foraging career. The redundancy provided by chemical navigation enhances the robustness of the bee's overall navigation system by providing independent confirmation of route information obtained through visual, celestial, and magnetic navigation methods. This redundancy creates navigation capabilities that remain reliable even when individual navigation systems encounter challenging conditions or temporary failures. Through the molecular messages that drift invisibly through the air around her, our honeybee maintains connection to a chemical information network that guides her navigation with sensitivity and precision that transforms every breeze into a carrier of spatial intelligence, creating navigation capabilities that operate through the fundamental chemistry of life itself, while providing practical guidance that enables successful completion of foraging journeys that sustain both individual survival and colony prosperity. Deep within the honeybee's remarkable brain, smaller than a sesame seed, yet capable of computational feats that challenge our understanding of biological intelligence, there exists a sophisticated mapping system that creates detailed mental representations of the three-dimensional world through which she navigates with such extraordinary precision. These internal maps represent one of nature's most impressive achievements in spatial cognition, transforming the continuous stream of sensory information gathered during flight into organized knowledge structures that preserve spatial relationships, remember successful routes, and enable planning of efficient flight paths through complex environments that may span several square miles of territory. The formation of cognitive maps begins during the bee's very first exploratory flights, as her developing spatial memory systems integrate visual landmarks, celestial compass readings, magnetic field information, and chemical signatures into coherent representations of spatial relationships that will guide navigation throughout her foraging career. These early mapping flights involve systematic exploration patterns that ensure comprehensive coverage of the area around the hive, while gathering the diverse sensory information needed to construct accurate and useful internal representations of the local environment. The neural architecture underlying the bee's mapping capabilities involves specialized brain regions that process spatial information and maintain organized representations of environmental relationships, despite operating within the severe size constraints imposed by the bee's tiny nervous system. These spatial processing centers demonstrate remarkable efficiency in storing and manipulating large amounts of geographic information while maintaining the processing speed necessary for real-time navigation during rapid flight through complex three-dimensional environments. The integration of multiple sensory inputs into unified spatial representations requires sophisticated neural processing that can combine visual landmark information with directional data from celestial and magnetic compass systems, distance measurements from flight time and energy expenditure, and chemical information from scent trails and floral signatures. This multi-sensory integration creates internal maps that incorporate far more information than any single sensory system could provide, resulting in comprehensive spatial awareness that exceeds the sum of individual navigation capabilities. The hierarchical organization of spatial memory allows the bee to maintain map information at multiple scales simultaneously, from fine-scale details about individual flower locations and landing approaches to broad-scale regional relationships that guide long-distance navigation between distant areas of her territory. This multi-scale mapping capability enables efficient navigation planning that can optimize routes at both local and regional levels while maintaining the flexibility to adjust flight paths based on current conditions and objectives. The updating mechanisms for cognitive maps enable the bee to maintain accurate spatial representations despite gradual changes in her environment caused by seasonal vegetation growth, weather damage, human activities, or the natural evolution of landscape features. These updating processes involve careful comparison between current sensory observations and stored map information, with mechanisms for incorporating new information while preserving the essential spatial relationships that provide navigation value. The route planning capabilities that emerge from sophisticated cognitive mapping enable the bee to evaluate multiple potential flight paths and select routes that optimize travel time, energy expenditure, and navigation reliability based on her stored knowledge of spatial relationships and past flight experiences. This planning capability demonstrates spatial reasoning that extends beyond simple point-to-point navigation to include complex optimization calculations that consider multiple factors affecting navigation success. The landmark relationship encoding within cognitive maps preserves not just the individual characteristics of visual navigation references, but also the spatial relationships between different landmarks that provide redundant navigation information and enable position triangulation based on multiple visual references. These landmark relationships create navigation capabilities that remain functional even when individual landmarks become temporarily obscured or unavailable. The temporal components of spatial memory allow the bee to associate different times of day, seasonal conditions, and environmental states with her spatial knowledge, creating time-dependent maps that account for how navigation conditions and resource availability change throughout daily and seasonal cycles. This temporal mapping enables navigation planning that anticipates changing conditions and selects strategies appropriate for current temporal contexts. The error detection and correction mechanisms within cognitive mapping systems enable the bee to identify inconsistencies between current sensory observations and stored spatial representations, triggering map updates and navigation adjustments that maintain accuracy despite environmental changes or temporary navigation errors. These error correction capabilities ensure that cognitive maps remain reliable navigation tools throughout the bee's foraging career. The compression algorithms used in spatial memory storage demonstrate remarkable efficiency in preserving essential navigation information while minimizing the neural storage requirements needed to maintain comprehensive spatial representations. These biological compression techniques extract and preserve the most important spatial relationships while discarding redundant or less critical information, enabling storage of vast amounts of geographic knowledge within severely constrained neural systems. The retrieval mechanisms for spatial information allow the bee to access relevant portions of her cognitive maps based on current location, navigation objectives, and environmental conditions, enabling rapid extraction of appropriate navigation guidance without overwhelming her limited neural processing capacity with irrelevant spatial information. This selective retrieval demonstrates sophisticated indexing and search capabilities within biological memory systems. The predictive capabilities of cognitive mapping enable the bee to anticipate upcoming landmarks, environmental features, and navigation challenges based on her current position and intended flight path, allowing proactive navigation adjustments that improve flight efficiency and reduce navigation errors. This predictive navigation demonstrates spatial reasoning that extends beyond reactive responses to current sensory input. The social components of map information may include spatial knowledge shared through dance communication and other social interactions, allowing individual cognitive maps to incorporate navigation discoveries made by other colony members and benefiting from collective exploration and route optimization. This social enhancement of spatial knowledge creates mapping capabilities that exceed what any individual bee could achieve through purely personal exploration. The optimization algorithms within cognitive mapping systems enable the bee to refine her spatial representations based on repeated flight experiences, gradually improving map accuracy and navigation efficiency through learning processes that identify and reinforce the most reliable spatial relationships while discarding or updating information that proves less useful for navigation purposes. The backup mapping systems provide alternative spatial representations that can maintain navigation capabilities when primary mapping systems encounter problems due to environmental challenges, memory errors, or neural processing difficulties. These backup systems demonstrate the biological wisdom of maintaining redundant spatial knowledge that ensures continued navigation function even under challenging conditions. The resolution scaling in cognitive maps allows the bee to represent spatial information at different levels of detail depending on the navigation requirements of specific areas, with frequently visited regions receiving high-resolution mapping while more distant or less important areas are represented with lower resolution that still provides adequate navigation guidance when needed. The geometric accuracy of cognitive maps enables the bee to maintain spatial representations that preserve essential geometric relationships between landmarks, routes, and destinations with sufficient precision to guide accurate navigation over distances that may span several miles. This geometric precision demonstrates sophisticated spatial processing capabilities that extract and preserve mathematically accurate relationships from sensory observations. The adaptive capabilities of cognitive mapping systems allow the bee to adjust her spatial representations and navigation strategies based on changing environmental conditions, seasonal variations, and evolving colony needs, ensuring that internal maps remain relevant and useful throughout the dynamic annual cycle of honeybee activity and environmental change. The memory consolidation processes that strengthen cognitive maps involve neural mechanisms that reinforce successful spatial associations while weakening connections that prove less reliable for navigation, creating increasingly accurate and efficient spatial representations that reflect the accumulated wisdom of extensive flight experience. The integration of cognitive maps with flight control systems enables the bee to translate spatial knowledge into appropriate motor commands that guide precise flight paths toward intended destinations, demonstrating sophisticated coordination between spatial cognition and motor control that enables seamless navigation through complex, three-dimensional environments. The computational efficiency of cognitive mapping demonstrates optimization strategies that achieve remarkable spatial reasoning capabilities while operating within the severe computational constraints imposed by the bee's tiny nervous system, revealing biological solutions to complex spatial processing challenges that may inspire advances in artificial intelligence and robotic navigation systems. The robustness of cognitive mapping systems ensures reliable navigation performance across diverse environmental conditions, seasonal changes, and varying flight objectives, demonstrating biological navigation capabilities that maintain consistent accuracy and efficiency despite the dynamic and unpredictable nature of natural environments. The learning protocols that guide cognitive map development involve systematic exploration strategies that ensure comprehensive spatial knowledge acquisition while minimizing the time and energy costs of map construction, demonstrating decision-making processes that balance the need for thorough spatial learning with the practical constraints of foraging efficiency and survival requirements. The spatial reasoning capabilities that emerge from sophisticated cognitive mapping enable the bee to solve complex navigation problems that require understanding of geometric relationships, distance calculations, and route optimization, demonstrating mathematical and logical reasoning abilities that challenge traditional assumptions about the cognitive capabilities of small-brained animals. Through the remarkable construction and maintenance of detailed internal maps that capture the essential spatial relationships of our complex three-dimensional world, our honeybee demonstrates that sophisticated spatial intelligence can emerge from neural systems of extraordinary efficiency and elegance, creating navigation capabilities that rival the most advanced technological systems while operating within biological constraints that require optimization strategies of breathtaking ingenuity and effectiveness. In the gentle rhythm of wing beats that carries our honeybee through the warm morning air, there exists a remarkable biological odometer that measures the distance of her journey with precision that rivals the most sophisticated technological instruments, while simultaneously maintaining an internal chronometer that tracks the passage of time with accuracy that enables her to calculate travel speed, estimate energy expenditure, and plan return flights that will bring her safely home before environmental conditions change or darkness falls. This integration of distance measurement and temporal awareness represents one of nature's most elegant solutions to the challenge of navigation in a three-dimensional world where accurate assessment of spatial and temporal relationships can mean the difference between successful foraging and becoming hopelessly lost. The biological mechanisms underlying distance measurement in honeybees operate through sophisticated integration of multiple sensory inputs that together create an internal system for tracking flight distance that functions with remarkable accuracy despite the complex three-dimensional flight paths and varying environmental conditions that characterize natural foraging behavior. This distance measurement capability enables the bee to maintain continuous awareness of her position relative to the hive while exploring new territory or navigating toward familiar destinations, providing essential information for route planning and energy management throughout extended foraging expeditions. The optic flow measurement system represents the primary mechanism through which the bee tracks her movement through space, as specialized visual processing systems monitor the rate at which visual patterns move across her visual field during flight, creating direct measurements of ground speed that can be integrated over time to calculate total distance traveled. This optic flow integration demonstrates remarkable computational capabilities that extract precise spatial information from the continuous stream of visual motion that characterizes high-speed flight through complex environments. The visual pattern recognition that enables accurate optic flow measurement involves sophisticated neural processing that can distinguish between visual motion caused by the bee's own movement through space and visual changes caused by moving objects in the environment, wind-induced vegetation movement, or other sources of visual motion that might otherwise interfere with accurate distance measurement. This motion discrimination ensures that the bee's distance measurement remains accurate even in dynamic environments with multiple sources of visual motion. The calibration of distance measurement systems occurs through processes that establish relationships between optic flow measurements and actual ground distances, accounting for factors like flight altitude, ground surface characteristics, and environmental conditions that affect the relationship between visual motion and spatial displacement. This calibration process demonstrates the bee's ability to maintain measurement accuracy across varying flight conditions and environmental contexts. The integration of distance measurement with directional navigation enables the bee to maintain vector tracking that preserves awareness of both distance and direction relative to the hive throughout her foraging journey, creating dead reckoning capabilities that provide continuous position updates even when navigating through unfamiliar territory where landmark references may be limited or unavailable. This vector integration represents sophisticated spatial reasoning that combines multiple navigation inputs into comprehensive position awareness. The temporal processing systems that enable accurate time measurement operate through internal biological clocks that maintain precise timing references despite the varying physiological demands and environmental conditions encountered during foraging flights. These biological chronometers demonstrate remarkable stability and accuracy, enabling time-based calculations that support navigation planning, energy management, and coordination with daily environmental cycles. The speed calculation capabilities that emerge from integrated distance and time measurement enable the bee to monitor her flight speed continuously and adjust her behavior based on current travel efficiency, environmental conditions, and energy expenditure rates. This speed awareness allows for real-time optimization of flight patterns that maximize foraging efficiency while ensuring adequate energy reserves for successful return flights to the hive. The energy expenditure estimation that relies on distance and time measurements enables the bee to monitor her energy consumption throughout foraging trips and make informed decisions about when to begin return flights, how far to venture from the hive, and whether to continue foraging or seek alternative food sources based on energy efficiency calculations. This energy awareness demonstrates sophisticated physiological monitoring and decision-making capabilities. The predictive calculations based on distance and time measurements allow the bee to estimate travel times for different flight paths, anticipate arrival times at known destinations, and plan foraging schedules that optimize resource collection while maintaining safety margins for unexpected delays or changing environmental conditions. This predictive capability demonstrates temporal reasoning that extends current measurements into future planning scenarios. The landmark distance encoding within the bee's spatial memory system preserves not just the identity and characteristics of visual navigation references, but also accurate measurements of distances between landmarks and from landmarks to important destinations like flower patches or the hive. This distance encoding creates spatial representations that include precise metric information rather than simple topological relationships. The route optimization algorithms that utilize distance and time measurements enable the bee to evaluate alternative flight paths and select routes that minimize travel time, reduce energy expenditure, or optimize other factors important for foraging success. These optimization calculations demonstrate mathematical reasoning capabilities that solve complex spatial problems involving multiple variables and competing objectives. The communication of distance information through waggle dance displays requires precise translation of measured flight distances into dance movement durations that accurately convey spatial information to observer bees, who must then translate dance timing back into their own distance estimates for successful navigation to advertise food sources. This distance communication demonstrates remarkable precision in both encoding and decoding spatial measurements. The environmental compensation mechanisms in distance measurement enable the bee to maintain accuracy despite varying environmental conditions that affect the relationship between flight effort and ground distance, including wind effects that can increase or decrease ground speed relative to air speed, altitude changes that affect visual references, and weather conditions that influence flight efficiency. The memory encoding of distance information enables the bee to preserve accurate spatial measurements in long-term memory systems that can guide future navigation decisions and route planning based on accumulated experience with different flight paths and destinations. This distance memory creates spatial knowledge that improves navigation efficiency through learning and experience. The error correction mechanisms in distance measurement provide capabilities for detecting and compensating for measurement errors that might accumulate during extended flights or under challenging environmental conditions, ensuring that distance tracking remains accurate throughout foraging expeditions that may involve complex flight paths and varying measurement conditions. The scaling of distance measurement systems enables accurate tracking across the full range of spatial scales encountered during honeybee foraging, from precise positioning during flower visits that require accuracy measured in centimeters to regional navigation that may involve flights spanning several miles from the hive. This scale flexibility ensures measurement accuracy across diverse navigation contexts. The integration of distance measurement with landmark navigation creates comprehensive spatial awareness that combines metric distance information with qualitative landmark recognition, enabling navigation strategies that utilize both precise measurements and distinctive visual references to maintain accurate position awareness throughout complex foraging expeditions. The temporal synchronization of distance measurement with environmental cycles enables the bee to coordinate her foraging activities with daily patterns of flower nectar availability, weather conditions, and other time-dependent factors that affect foraging success, demonstrating integration between spatial navigation and temporal environmental awareness. The backup measurement systems provide alternative methods for distance tracking when primary systems encounter difficulties due to environmental conditions, equipment limitations, or measurement errors, ensuring continued navigation capability even when individual measurement systems are temporarily compromised or unavailable. The resolution of distance measurement enables detection of spatial changes and position variations with precision that supports accurate navigation even during complex flight maneuvers, precise flower approaches, and detailed exploration of small-scale environmental features that require fine-scale spatial awareness and control. The computational efficiency of distance and time measurement systems enables these calculations to operate continuously throughout flight without overwhelming the bee's limited neural processing capacity or interfering with other essential cognitive functions like obstacle avoidance, flower recognition, and environmental monitoring. The learning enhancement through distance and time experience allows the bee to improve her measurement accuracy and navigation efficiency through repeated exposure to different flight conditions and environmental contexts, creating accumulated expertise that enhances navigation performance throughout her foraging career. The social coordination of distance and time information enables multiple bees to share temporal and spatial knowledge through dance communication and other social interactions, creating collective awareness of flight times, distances, and optimal scheduling that benefits the entire colony's foraging efficiency and resource collection. The adaptation of measurement systems to individual differences accommodates variations in flight speed, visual processing capabilities, and physiological characteristics that affect distance and time measurement accuracy, ensuring that each bee can maintain effective navigation despite individual differences in sensory and motor capabilities. The robustness of distance and time measurement ensures reliable navigation performance across diverse environmental conditions, seasonal changes, and varying flight objectives, demonstrating measurement capabilities that maintain accuracy and consistency despite the dynamic and unpredictable nature of natural foraging environments. The precision of temporal calculations enables the bee to coordinate her activities with remarkable accuracy, timing her departure from the hive, estimating arrival times at distant flower patches, and planning return flights that account for changing environmental conditions and the need to complete foraging activities within available daylight hours. The integration of measurement data with decision-making processes enables the bee to use distance and time information for complex navigation choices that balance multiple factors, including energy efficiency, resource quality, environmental conditions, and colony needs, demonstrating sophisticated reasoning capabilities that optimize foraging outcomes. The mathematical relationships underlying distance and time measurement demonstrate computational abilities that enable the bee to perform complex calculations involving rates, ratios, and optimization problems that require mathematical reasoning traditionally associated with much more complex nervous systems and cognitive architectures. Through the precise measurement of distance traveled and time elapsed during her foraging journeys, our honeybee maintains quantitative awareness of her spatial and temporal position that enables navigation planning of remarkable sophistication and accuracy, demonstrating how biological systems can achieve measurement precision that rivals technological instruments, while operating within the elegant constraints of natural selection and evolutionary optimization that create measurement capabilities of extraordinary efficiency and reliability. Drifting through the peaceful morning air that surrounds our honeybee like an invisible ocean filled with currents, pressure variations, and atmospheric phenomena that constantly influence every aspect of her navigation experience. The ever-changing world of weather presents both challenges and opportunities that require sophisticated adaptation strategies, enabling her to maintain navigation accuracy despite conditions that could dramatically alter flight dynamics, visibility, sensory reliability, and the fundamental relationship between intended flight paths and actual movement through three-dimensional space. The bee's remarkable ability to adapt her navigation systems to accommodate weather variations demonstrates biological flexibility and resilience that enables successful foraging across the full range of environmental conditions that characterize the dynamic atmospheric world through which she must navigate to survive and thrive. The atmospheric pressure changes that accompany different weather patterns create variations in air density that affect the bee's flight performance, energy expenditure, and the relationship between wing beat frequency and forward progress through the air, requiring continuous adjustments to flight behavior and navigation calculations that account for how changing atmospheric conditions influence the fundamental physics of flight. These pressure adaptations demonstrate the bee's sophisticated awareness of atmospheric conditions and her ability to modify flight strategies to maintain navigation efficiency despite environmental changes that would challenge rigid navigation systems incapable of dynamic adjustment. The wind patterns that characterize different weather conditions present complex navigation challenges that require the bee to distinguish between her intended flight direction and her actual movement relative to the ground, as air currents can carry her off course, increase or decrease her effective ground speed, and create drift effects that must be compensated through continuous course corrections based on visual references, celestial navigation, and other guidance systems that remain reliable despite wind-induced displacement. This wind compensation demonstrates sophisticated spatial reasoning that integrates multiple navigation inputs to maintain accurate course tracking despite atmospheric forces that constantly influence flight trajectories. The visibility variations associated with different weather conditions require adaptive strategies that enable the bee to maintain navigation accuracy. When cloud cover obscures celestial references, atmospheric haze reduces landmark visibility, or precipitation creates visual conditions that compromise normal landmark recognition and distance measurement systems. These visibility adaptations involve shifting between different navigation strategies, depending on current atmospheric conditions, demonstrating flexibility that ensures continued navigation capability across diverse weather scenarios. The humidity effects that accompany changing weather patterns influence the bee's perception of chemical navigation signals, as moisture levels affect the volatility, concentration, and dispersal patterns of scent trails and floral aromas that provide important navigation information, requiring adjustments to chemical navigation strategies that account for how atmospheric moisture affects the reliability and range of olfactory guidance systems. This humidity adaptation demonstrates the bee's ability to modulate her reliance on different navigation systems based on current atmospheric conditions that affect their effectiveness. The temperature variations that characterize different weather conditions affect multiple aspects of the bee's navigation experience, from the physiological efficiency of flight muscles and nervous system function to the environmental behavior of landmarks, chemical signals, and atmospheric conditions that influence navigation system performance, requiring thermal adaptations that maintain navigation accuracy across the range of temperatures encountered during normal foraging activities. These temperature compensations demonstrate biological regulation systems that preserve navigation function despite thermal challenges that could compromise sensitive biological processes. The precipitation challenges that occur during rain or snow events create navigation conditions that can severely compromise visual navigation systems while also affecting flight stability, energy expenditure, and the bee's ability to maintain normal flight patterns and navigation behaviors, requiring specialized strategies for either continuing navigation during mild precipitation or seeking shelter and delaying foraging activities until conditions improve. These precipitation responses demonstrate decision-making capabilities that balance navigation necessity with safety considerations and energy conservation. The cloud cover adaptations that enable navigation when celestial references become obscured involve shifting primary reliance from sun compass navigation to alternative systems like landmark recognition, magnetic sensing, and dead reckoning that can maintain directional accuracy when direct solar observation becomes impossible, while also utilizing polarization patterns in skylight that may remain detectable even when the sun itself is hidden behind clouds. These celestial backup strategies demonstrate redundancy planning that ensures continued navigation capability when primary celestial navigation systems encounter atmospheric interference. The atmospheric turbulent compensation that enables stable navigation during windy conditions involves flight control adjustments that maintain course accuracy despite air currents that create unpredictable forces on the bee's flight path, requiring constant micro-adjustments to wing position, flight speed, and navigation corrections that preserve intended flight direction despite atmospheric disturbances that could otherwise compromise navigation precision. This turbulence management demonstrates sophisticated integration between navigation planning and flight control systems. The barometric pressure sensitivity that enables the bee to detect and respond to approaching weather changes involves physiological sensing capabilities that can perceive atmospheric pressure variations associated with developing weather systems, enabling proactive navigation planning that accounts for expected changes in flying conditions and allows for strategic timing of foraging activities that avoid periods of challenging weather. This pressure sensing demonstrates predictive capabilities that extend navigation planning beyond current conditions to anticipated future scenarios. The seasonal weather adaptation that enables navigation across the full annual cycle involves adjustments to navigation strategies, timing patterns, and weather tolerance that account for the different atmospheric conditions, daylight patterns, and environmental challenges that characterize different seasons, ensuring that navigation capabilities remain effective from spring emergence through fall preparation periods despite dramatic seasonal changes in weather patterns and environmental conditions. These seasonal adaptations demonstrate long-term flexibility that maintains navigation effectiveness across diverse temporal contexts. The micrometeorological awareness that enables navigation through locally varying weather conditions involves sensitivity to small-scale atmospheric phenomena like thermal updrafts, valley wind patterns, and localized precipitation that can create dramatically different flying conditions within short distances, requiring navigation strategies that account for spatial variations in atmospheric conditions and enable efficient flight path planning through areas with diverse microclimatic characteristics. This microweather awareness demonstrates sophisticated environmental assessment capabilities that operate at multiple spatial scales simultaneously. The wind direction utilization that enables energy-efficient navigation involves strategic planning that takes advantage of favorable wind patterns while minimizing the impact of adverse conditions, including route selection that maximizes tailwind assistance during outbound flights, timing strategies that avoid periods of strong headwinds, and altitude selection that utilizes different wind patterns that may exist at different heights above ground. This wind strategy demonstrates optimization planning that integrates atmospheric conditions with navigation objectives to improve overall foraging efficiency. The storm avoidance behaviors that protect the bee from dangerous weather conditions involve early detection of approaching severe weather through atmospheric pressure changes, visual observation of developing cloud formations, and other environmental cues that enable proactive shelter seeking or early return flights that avoid exposure to conditions that could compromise flight safety or navigation capability. These storm responses demonstrate survival prioritization that balances foraging objectives with weather-related safety considerations. The altitude adjustment strategies that enable navigation across different atmospheric layers involve flight planning that accounts for how atmospheric conditions vary with height above ground, including wind speed and direction changes, temperature gradients, and visibility conditions that may differ significantly between ground level and higher altitudes, enabling selection of flight levels that optimize navigation conditions for current weather scenarios. These altitude strategies demonstrate three-dimensional weather awareness that extends navigation planning into the vertical dimension of atmospheric variation. The thermal sensing capabilities that enable detection of atmospheric temperature patterns involve physiological systems that can perceive thermal gradients, warm and cool air masses, and temperature variations that indicate different atmospheric conditions, enabling navigation strategies that take advantage of favorable thermal conditions while avoiding areas where temperature extremes might compromise flight performance or navigation system function. This thermal awareness demonstrates multisensory environmental assessment that incorporates temperature information into comprehensive weather evaluation. The humidity compensation mechanisms that maintain navigation accuracy across varying moisture conditions involve adjustments to chemical navigation sensitivity, visual processing adaptations that account for atmospheric haze effects, and behavioral modifications that optimize navigation performance under different humidity levels, ensuring that navigation systems remain reliable despite atmospheric moisture variations that could otherwise affect sensory system performance. These humidity adaptations demonstrate physiological flexibility that preserves navigation function across diverse atmospheric conditions. The lightning and electromagnetic disturbance response that protects navigation systems from atmospheric electrical activity involves behavioral strategies for avoiding areas of electrical storm activity and potential physiological adaptations that protect sensitive magnetic navigation systems from electromagnetic interference associated with lightning and other atmospheric electrical phenomena. These electromagnetic responses demonstrate awareness of atmospheric electrical conditions and protective strategies that preserve navigation system integrity. The air pressure navigation involves using atmospheric pressure variations as additional navigation information that can supplement other guidance systems, with pressure differences potentially providing information about altitude changes, geographic features, and atmospheric conditions that enhance overall navigation awareness and provide backup guidance when other navigation systems encounter difficulties. This pressure navigation demonstrates utilization of atmospheric conditions as navigation resources rather than simply environmental challenges to overcome. The wind mapping capabilities that enable efficient navigation through varying atmospheric conditions involve memory systems that preserve information about local wind patterns, seasonal wind variations, and geographic features that influence air movement, creating accumulated knowledge about atmospheric behavior that guides flight planning and route selection, based on expected wind conditions rather than simply reactive responses to current atmospheric conditions. This wind knowledge demonstrates long-term environmental learning that improves navigation efficiency through accumulated atmospheric experience. The weather prediction abilities that enable proactive navigation planning involve integration of multiple atmospheric indicators, including pressure changes, wind shifts, cloud formations, and other environmental cues that provide advance warning of changing weather conditions, enabling strategic planning that optimizes foraging activities based on anticipated atmospheric conditions rather than simply reactive responses to current weather. This weather forecasting demonstrates predictive environmental assessment that extends navigation planning beyond immediate conditions. The energy conservation strategies during challenging weather involve behavioral adaptations that minimize energy expenditure when atmospheric conditions create increased flight costs, including modified flight patterns that reduce exposure to adverse wind conditions, altered foraging strategies that account for increased energy costs of navigation under challenging weather, and timing adjustments that concentrate flying activities during periods of favorable atmospheric conditions. These energy adaptations demonstrate resource management that integrates atmospheric conditions with physiological constraints. The communication of weather information within the colony may involve behavioral signals that inform other bees about current atmospheric conditions, weather-related foraging challenges, or favorable weather windows that enhance foraging success, creating social weather awareness that benefits collective navigation planning and resource allocation strategies. This weather communication demonstrates social coordination that extends individual weather awareness to colony-level atmospheric intelligence. The recovery strategies for weather-related navigation errors involve behavioral adaptations that enable course correction when adverse weather conditions have compromised normal navigation accuracy, including increased reliance on backup navigation systems, enhanced attention to reliable navigation cues, and conservative navigation strategies that prioritize safety over efficiency when weather conditions create elevated navigation risks. These recovery strategies demonstrate adaptive flexibility that maintains navigation capability even when challenging weather has compromised normal navigation performance. The weather-dependent timing strategies that optimize foraging success involve behavioral patterns that synchronize activity periods with favorable atmospheric conditions, including daily timing that takes advantage of calm morning air before afternoon wind development, seasonal timing that coordinates activity with predictable weather patterns, and opportunistic timing that maximizes foraging efficiency during unexpected weather improvements. These timing strategies demonstrate temporal coordination with atmospheric cycles that optimizes navigation success across multiple timescales. The microhabitat weather assessment that enables navigation through locally varying atmospheric conditions involves sensitivity to small-scale environmental features that create distinctive weather patterns, including forest edge effects that influence wind patterns, topographic features that create thermal variations, and water body influences that affect local humidity and temperature conditions. This microhabitat weather awareness demonstrates fine-scale environmental discrimination that enables navigation optimization at very local spatial scales. The adaptive navigation flexibility that enables success across diverse weather conditions demonstrates the remarkable resilience of biological navigation systems that can maintain function despite atmospheric challenges that would disable rigid technological systems, revealing optimization strategies that balance accuracy with adaptability and precision with robustness to create navigation capabilities that remain effective across the full range of atmospheric conditions encountered in natural environments. This weather adaptability demonstrates the evolutionary wisdom of navigation systems that prioritize survival and continued function over theoretical optimal performance under ideal conditions. Through her sophisticated adaptation to the ever-changing atmospheric world that surrounds her during every flight, our honeybee demonstrates that successful navigation requires not rigid adherence to fixed strategies, but rather flexible integration of multiple navigation systems with real-time environmental assessment, that enables continuous adaptation to atmospheric conditions that present both challenges and opportunities for efficient flight and accurate guidance through the dynamic three-dimensional world of weather and wind that characterizes the atmospheric ocean through which she must navigate to achieve her foraging objectives while maintaining the safety margins necessary for successful return to the colony that depends on her navigation success. As the golden afternoon sun begins its gentle descent toward the western horizon, casting longer shadows across the peaceful meadow where our honeybee has spent her day exploring the intricate world of flowers and navigation challenges, the time arrives for perhaps the most critical demonstration of all her remarkable navigation abilities, the journey home. This return flight represents the culmination of everything she has learned and experienced during her foraging expedition, requiring the precise integration of all her navigation systems working in perfect harmony to guide her safely back to the hive that represents not just her destination, but her entire world of social connections, stored resources, and the warm community of sisters who depend on her successful return. The preparation for the homeward journey begins with a comprehensive assessment of her current situation, as the bee evaluates her position relative to familiar landmarks, checks her internal compass readings against the sun's current position, and estimates the distance and direction to her home based on the accumulated navigation data she has gathered throughout her day of exploration and foraging. This pre-flight assessment demonstrates the remarkable integration of multiple navigation systems that must work together seamlessly to provide accurate guidance for what may be the most important flight of her day. The route planning for her return journey involves sophisticated decision-making that balances multiple factors, including the most direct path home, the energy efficiency of different flight options, the reliability of navigation references along various routes, and the current weather conditions that might affect flight safety and navigation accuracy during her homeward flight. This route optimization demonstrates spatial reasoning capabilities that evaluate complex navigation scenarios and select strategies that maximize the probability of successful completion of her journey, while minimizing unnecessary risks or energy expenditure. The departure from her final foraging location requires careful orientation that establishes accurate initial heading based on her knowledge of the direction toward home, taking into account any environmental factors that might affect her early flight path, and ensuring that her navigation systems are properly calibrated for the changing conditions that may exist during the late afternoon period when atmospheric conditions often differ from those that existed during her morning departure from the hive. The celestial navigation adjustments that guide her homeward flight must account for the significant changes in the sun's position that have occurred during her day away from the hive, requiring temporal compensation that adjusts her sun compass readings for the solar movement that has taken place while she was foraging, demonstrating the sophisticated chronometer capabilities that enable accurate celestial navigation despite the dynamic nature of solar position throughout the day. The landmark recognition sequence that unfolds during her return flight involves the systematic identification of familiar visual references that confirm her navigation accuracy and provide opportunities for course corrections if any navigation errors have accumulated during her journey, creating a chain of visual confirmations that guide her progressively closer to home while building confidence in her navigation accuracy through repeated verification of her position and heading. The distance monitoring that continues throughout her homeward flight enables her to track her progress toward the hive and estimate her arrival time based on current flight speed and remaining distance, providing information that helps her manage her energy reserves and maintain appropriate flight efficiency for successful completion of her journey without exhausting her physical capabilities before reaching her destination. The environmental awareness that characterizes her return flight includes continuous monitoring of weather conditions, wind patterns, and atmospheric changes that might affect her flight performance or navigation accuracy, enabling proactive adjustments to her flight strategy that maintain optimal progress toward home despite any environmental challenges that may arise during her homeward journey. The backup navigation activation that may occur during challenging portions of her return flight demonstrates the redundancy and reliability of biological navigation systems that can shift between different guidance methods depending on current conditions and navigation requirements. ensuring that she maintains accurate heading toward home even when individual navigation systems encounter temporary difficulties or environmental interference.